push that rock here with Simpson math. Let's talk about rational functions, which are ratios, hence the word rational, of polynomials. We want to ask questions and investigate and find the answers like these. What do the graphs of rationals look like? How do rational functions behave? This is a highly varied answer, and the answer to this question is depends. And the first big thing you worry about is, ouch, wait, we're dividing, right? Ratios create division, and division creates domain issues, because what is the one number we cannot divide by? So here is maybe what we might think of as sort of a parent. It's not really, but it's sort of a parent rational function, the reciprocal function. If I'd put this -1 over here, we'd be talking inverse, right? But no, over here with x represents numbers, inputs. So therefore, this just means some number to the -1 power, which of course means reciprocate. So the -1 power with a number is reciprocation. So we reciprocated. So this reciprocal function, what does it mean? If I put a -5 in here, well, the reciprocal of a -5 is a -1/5. The reciprocal of -2 is a -1/2, and then a -1. Ooh, what is the reciprocal of a -1/2? And how many negative halves go into 1? Well, the answer is -2. And so then we get -5, and then we get -10. And we're noticing something. The closer we get to 0, the further away the output is from 0. But the further away we get from 0 with the inputs, the closer the outputs are to 0. Is that going to happen on the positive side? Well, of course. How many tenths are in 1? Well, 10 of them. Or what is the reciprocal of 1/10? That is 10. The reciprocal of 1/5 is 5, 2, and then 1, and then 1/2, and then 1/5. So the further away the inputs get from 0, the closer the outputs get to 0. But the closer the inputs get to 0, the further away those outputs get from 0. So let's look at the graph of this thing. So remember, over at 5, it was 1/5, and at -5, see 1, 2, 3, 4, 5, it was a -1/5. Then at 1, it was 1, and at -1, it was a -1. At 2, it was a half. At -2, it was a -1/2. Then remember, at a half, it was 2. But at a tenth, really close here, it was way up, well, let's not go to 10. Let's do a fifth. Well, that's still really close here, and it's at 5. And a -1/5, it was at -5. So what does the graph look like? Well, it seems to be getting, remember, the closer we get to 0, the larger it gets. Whoa, what is that? Now, there's a fundamental, oh, I can't draw one-handed, sorry. We have two types of isotopes here. We have an isotope on the x-axis, y equals 0, called an end-behavior isotope. It happens to be a horizontal isotope, meaning a flat line that's horizontal. The graph will get closer and closer to it. It will mimic the x-axis as the x values get large. Same thing happens out here, of course. So as the x values go out to -infinity, the graph will start to mimic the x-axis. It's never perfectly flat, but it'll look sort of flat out here. Okay, so that's an end behavior isotope. Then we have this strange vertical isotope that's happening at the domain restriction, because I didn't mention that, but I should have. 0 is undefined because 0 is the one number that does not have a multiplicative inverse or a reciprocal, because 1 over 0 is undefined. So I cannot put 0 into the function, so I should have no output on the y-axis, because 0 cannot be put into this function. But as we get close to 0, we saw the y values go up. This is why Bhaskara said he defined 1 over 0 to be equal to infinity. He was envisioning exactly this situation. This is not true in modern mathematics. This is not a thing, okay? This is not a deal in modern mathematics, so I hesitate to write it down. But we play around with this idea, or an Indian mathematician in the 800s played around with this idea, because the closer we get to 0, when we divide 1 by numbers closer and closer to 0, the bigger and bigger it gets. And of course, it goes up and up and up, and you will approach infinity. In calculus, we say the limit as the x values go to 0 from the right is infinity. So Remember our questions. What do the graphs of rational functions look like? Well, here's a rational function. How does it behave? Well, it's decreasing on this side. It's also decreasing on this side, but there's a distinct break in the graph. There's a place where you have to pick up your pencil. We call it a discontinuity because 0 is not in the domain, because division by 0 is not defined. Now, do all rational functions look like this? Let's think about this rational function. Here we have a cubic divided by a linear. Okay, that's quite a bit different from having 1 over x, which was a 0 degree polynomial over a first degree. We have a third degree polynomial over a first degree now. Well, I'm going to simplify this some. I'm going to factor the top. You want to factor when you see a polynomial like this, if you can. I'm going to factor by grouping, which means I'm going to look at the first two terms and see if there's a common factor, and it's x squared, factor it out. Look at the second two terms, see if there's a common factor, factor it out. Now I'm going to factor out the common factor of x minus 1. That leaves me x squared and 7. So I have factored the numerator by grouping. So this is the same as this. If I multiply these two binomials out, I will get this 4-term third degree polynomial. Now, we're going to want to reduce, but before we reduce, we need to notice the domain. What is the domain? Well, the domain is any real number except 1. We cannot put in 1, because if we put in 1, 1 minus 1 is 0, and we cannot divide by 0. Okay? Even though we'd have a 0 up here, you can't cancel out a 0 into it. 0 doesn't go into 0. That's not a thing. Okay, so you cannot put 1 into this function. So the domain is from negative infinity up to 1, and then from 1 to infinity, and we use parentheses because the 1 is not included. Now we can reduce, and we see that this function, other than this domain restriction, looks like a polynomial that's x squared plus 7. Well, we can graph x squared plus 7. That just means we went up 7. The parabola went up 7, so there should be a point. Wait a minute, I can't put in 1. There should be a point here, but I can't put it in. Okay, there should be a point here, and it should be a parabola that looks like so. But remember, we had a domain restriction at 1. So it looks exactly like a parabola, except that at 1, there's no output. We represent the fact that there's no output with this hole, but you actually can't see it, of course, because points don't have dimension. They don't have any kind of size. But we represent it with this little open dot to show that the domain restriction. So for anybody looking at it, realizes, okay, it's a parabola, except it's missing that point. So what do rational functions look like? They can look like polynomials. This looks like a second degree polynomial. It looks like it's just a quadratic shifted up, but it has a hole. One last example for this video. Here's a z degree polynomial divided by second degree polynomial. If I put in negative 5 and I square it, I get 25 plus 1, which is 26, so that's 5 over 26. That's roughly 1/5, because if this was 25, it would reduce to 1/5, which is roughly 0.2. If I put in a negative 1 and square it, I get 1 plus 1 is 2, so that's 5 halves, which is 2.5. If I put in a negative half and square it, I get a fourth, so that's 1.25. So we have 5 over, let's see, that's 1 and a fourth, so that'd be 5/4. Now, when I simplify this, it's 5 times the reciprocal 4/5, and so I get 4. When I put in 0, is 0 allowed to put in? Yeah, of course, I can put in 0. 0 squared plus 1 is 1, and I get out 5. When I put in a half, I get the same thing I did when I got a negative half, because when you square it, you get a fourth, just like we did before. So all of these outputs here are going to be those outputs there. So I'm going to have 4 and 2.5 and roughly 0.2. Now, is there a domain issue? It's division, but notice x squared plus 1 never equals 0. So the domain is still all real numbers. So just because it's a rational function doesn't mean that it for sure has domain issues. This rational function does not have any kind of domain issue. So let's graph that last one. At 0, it was 5. At I need to look at the points. I've forgotten them already. At 1 and -1, it was 2.5. At a half, it was 4. And -half, it was 4. And then when we went out to 5, it was 1/5 or close to 1/5. And so we have a function looking like this. So this doesn't have any holes in it, like our previous example. It doesn't have any vertical asymptotes, but it does clearly seem to have a end behavior asymptote. So once again, it seems that as the x values get really big, we're going to be dividing 5 by really big numbers, and so it's going to get smaller and smaller. And so it's going to have a horizontal asymptote or an end behavior asymptote that's flat, and is y equals 0, meaning the graph will begin to mimic the behavior of this x-axis or this flat line at y equals 0 when the x values get really big. But no domain issues, no vertical asymptotes, no holes whatsoever. Math made simple. It's Simpson math.